All right, class. Well, we're going to continue on with the matrix operations. So we went over addition and subtraction and scalar multiplication in the last video, but just to review, so scalar multiplication of a matrix is if we just take some constant. In this case, this is the constant we have is 2, and we have the multiplying out the basic 2 by 2 matrix 1, 2, 3, and 4. We're going to come back and forth with this matrix. This is a pretty popular one I like to use in examples, but whenever you have a scalar in front of a matrix like this, when you multiply it out, you're going to be multiplying every single element by that value. So this is going to be equal to 2, 4, 6, and 8. All right. Okay. We can do something called multiplication by a row matrix. So we can multiply a row matrix times a column matrix, but the dimensions matter here. All right. So we can have a row matrix times a column matrix. And the example we have in the notes is 1, 2, 4 times the column matrix -1, 0, and 3. Now this works because of the dimensions here. All right, so this is a 1 row by 3 column matrix, so it's actually 1 by 3. And this column matrix is 3 rows by 1 column. So this is a 3 by 1. So whenever you multiply matrices like this together, you can look at the dimensions and it'll tell you what the dimension of the resulting matrix is going to be. All you have to do is get rid of the inside value here, and what you'll see is that that becomes a 1 by 1 matrix, or a constant. And this is essentially similar to what we did with the vector dot product. All right, so this is going to be equal to a scalar, and that's -1 plus 0 plus 12, which is just 11. All right. Now look what happens when we reverse the order of multiplication, though. So if we take that column vector and multiply it by the row vector instead, so 1, 0, 3 times 1, 2, 4, now the dimensions are different. So this now becomes a 3, this is a 3 by 1 matrix here, and this is a 1 by 3 matrix here. So the result is now going to be a 3 by 3 matrix. All right? And when we go ahead and multiply this out, we get the following matrix here. So we know it's going to be a 3 by 3, so let's just start the border there. So we're going to have -1, all right, -2, -4. Now this is going to have all zeros along the second row, so it's 0 times 1, 0 times 2, and 0 times 4, so these are all zeros here. And then 3 times 1 is 3, 3 times 2 is 6, and then 3 times 4 is 12. So that's our resulting matrix there. All right. We have a very important matrix called the identity matrix, and this is the matrix equivalent of the number 1. But the identity matrix is always going to have 1s on all the diagonals and 0s elsewhere. So there's going to be 1s here, and then we're going to have 0s everywhere else. So 0, 0, 0, 0, 0. All right. These are all zeros. So that's the key important component, is that there's 1s along the diagonal. And this is the matrix equivalent of the number 1. Let's show that. So if we have that matrix we always use, 1, 2, 3, 4, and we multiply it by the identity matrix 1, 0, 0, 1, we're going to get the following. It's 1 times 1 plus 2 times 0 is 1. 1 times 0 plus 2 times 1 is 0. 3 times 1 plus 4 times 0. Wait. What am I doing wrong here? I was doing something wrong. I think yeah. This is, let me see here. Now this is right. I'm second guessing myself here. All right, 1 times 1 plus 2 times 0 is 1. 1 times 0 plus 2 times 1 is 2, not 0. And 3 times 1 plus 4 times 0 is 3. And then 3 times 0 plus 4 times 1 is 4. My apologies. And you can see that we get the same matrix back. If we multiply this the other way around, it's the same thing as 1, 0, 0, 1 times 1, 2, 3, 4. And you get the exact same. So with the identity matrix, the multiplication can commute. Now we can do a couple of operations on the identity matrix. Let's say we want to swap the two columns. So swapping columns. So instead of 1, 0, 0, 1, let's say we go to 0, 1, 1, 0. All right. Now what happens to our matrix 1, 2, 3, 4 when we multiply by that new identity matrix? Well, let's multiply it out. And hold on, something under this paper here. So that's 1 times 0 is 0, plus 2 times 1 is 2. Okay. 1 times 1 is 1, plus 2 times 0 is 1. And then 3 times 0 is 0, plus 4 times 1 is 4. And then 3 times 1 is 3, plus 4 times 0 is 3. All right. So what you can see here is that this is the same thing as the matrix we started with, but with the columns swapped. So if we take the identity matrix and perform an operation on it, when we multiply any other matrix by that identity matrix, it mimics that operation. Okay, pretty handy tool there. All right. So like I mentioned in general, matrix multiplication is non-commutative, which means that matrix A times matrix B is not necessarily, or not the same as matrix B times matrix A. Clearly you can see we did that up here, where we've got matrix A times matrix B, let's say, hypothetically, and then matrix B times matrix A. We got completely different results here. We have a scalar up here, or a matrix with one entry, and then down here we had a 3 by 3 matrix. These are definitely not the same thing, and all we did was we swapped the order here. Okay. We can do an operation called the transpose of a matrix. And what this does is it swaps the columns for the rows. So let's say we have A is equal to A, B, C, D. And that means that A transpose, so you can see we typically annotate that with a little capital T in the superscript. That's going to be, you take the first column, that becomes the first row. So it goes A and C, and the second column, B and D, becomes the second row, B and D, like that. Okay. There's a couple of other matrices, such as diagonal matrices, upper triangular matrices. Those are in the notes. Essentially, a diagonal matrix is a matrix with, it's like the identity matrix. There's values along the diagonal, and everything else is 0. And then an upper triangular matrix has values along the diagonal and positive values above or non-zero elements above the diagonal and zeros below. And then obviously a lower triangular matrix would be the other way around, but I'll let you defer to the notes for that. Okay, now we can start a discussion on matrix inverses. So the inverse of a matrix, let's define what the inverse of a matrix is. So if we have two matrices A and B, so if matrix A times matrix B ends up being equal to the identity matrix, then that implies that matrix B is actually the inverse of matrix A. Whoops, -1. Should be a -1 up there. All right, so the inverse, so essentially A times A inverse gives us the identity matrix. In scalar terms, this is the same thing as, you know, the number 2 times the number 1 over 2 gives us the number 1, right? You know, if you want to think of it in terms of scalars, but, you know, that's just a tool. It's not necessarily the same thing, so don't focus on that. But the idea here is that if you take a matrix A and you multiply it by its inverse, it takes you, or it results in the identity matrix. And that's kind of going to be, it's going to be a little handy for us here. So if we've got our matrix 1, 2, 3, 4, and we multiply it by some other matrix, A, B, C, D, then it's going to give us this identity matrix 1, 0, 0, 1. And then this matrix, by definition, is the identity, the inverse, all right, of this matrix here. All right. So why is this all handy? Well, if we have that system of equations where we had A, 1, 1, well, let's do it this way. Before we put it into matrix notation. We did this on the last video where we had A1, 1 times x1 plus A1, 2 times x2 plus A1 n times xn, that's equal to B1. And then we had A2, 1 x2, x1 plus A2, 2 x2 plus A2n xn equals B2. We can go all the way down to an1 x1 plus an2 x2 plus ann times xn equals bn, where n is the dimension of matrix of the system. So if we've got 4 equations, we're going to have 4 unknowns. So you can see this is going to be 4 by 4. Row 4, entry, column 4, that entry there. When we took this and wrote it into the system in matrix form as such, we had it as A1, 1, A1, 2, all the way out to A1, n. And this was A2, 1, A2, 2, all the way out to A2, n. And went down to AN1, AN2, ANN. And then what we did was we factored out the x's, x1, x2, xn. And that was equal to b1, b2, bn. All right, so this is some matrix A, this is some vector x, and this is some vector b. The idea here is if we can figure out what the inverse of this is, so if we can get then we can very easily solve this system. Okay. Then we have A times X is equal to B. If we left multiply by the inverse, A inverse times A times X is equal to A inverse times B. Because what we do to the left-hand side, we have to do to the right-hand side. So if we're multiplying this way by the inverse, we have to multiply both sides by that. So this just becomes the identity matrix times vector X is equal to A inverse times vector B. And that gives us the solution. So the solution for X is just going to be A inverse times the vector B. So we need to find A inverse, and then we can solve this entire system out in one fell swoop, right? It beats trying to solve using Gaussian elimination every row, right? That could be a lot of what are called flops, which is essentially operations to try to solve linear equations like this. Right? If we could just define what the inverse is, we could just take the dot product, and essentially this is how computers actually solve systems like this. So we need this A inverse, right? Okay. So this isn't going to be easy to just, there's no single magic formula for this. This isn't going to be very easy to just describe. So I'm going to do this with examples. So before that, though, we should go over a couple of, so this might actually be, how to solve this might be in a subsequent lecture, actually. So we're going to do elementary matrices now, and then we'll talk about determinants in the next video, but I don't want to overwhelm you guys. So let's look at elementary matrices now. So elementary matrices. We symbolize these with a bold-faced E, all right? And we will typically have, three operations that primarily they use that when we use those three operations, we can solve out any system, or we can reduce any matrix into a way that makes it easy to interpret the answers on the this X vector. Let me back up a little bit. Makes it really, really easy to understand what the values of X are going to be. Right? So the three operations are, we have one, which is swapping rows or interchanging rows. We have a second operation, which is taking one row and adding a multiple of another row to it. So adding a multiple of one row to a different one. Oops, one row to another. And don't forget, when we say adding a multiple, that multiple can be multiplying by the -1. So we can allow for subtraction here with this number 2. All right. And then number 3 is multiplying a row by a non-zero scalar. All right, so let's describe the notation of these things here. So we have E I comma J of R. All right, so that elementary matrix is going to be, we're going to add R times row I to row j. We can have this matrix here, I, comma, j. That is going to give us a matrix which switches rows I and j. So we're going to switch row I with j. And then lastly, we have E I of R. And that's just multiplying row I by a factor of R. And we're going to do this to the identity matrix. So that's what we're going to start off with. We're going to start off with the identity matrix. All right, let's just do a 2 by 2 case. All right. And so we can hypothetically, we can say, all right, what would let's follow the notes, E2 of 5b, right? So here it corresponds to this operation here. We're going to take, we're going to multiply row 2 by the value 5, okay? So that is going to give us 1, 0, 0, and then 5 now, okay? And if we multiply 1, 2, 3, 4. If we multiply our basic demonstration matrix here by that elementary matrix, all right, so again, this is E2 of 5, all right, let's just do the math and see what we get. So it's 1 plus 0 is 1, 2 plus 0 is 2, 0 plus 15 is 15, and then 0 plus 20 is 20. Does that correspond to multiplying the second row by 5? Yeah, 3 times 5 is 15, 4 times 5 is 20. The first row is left untouched, all right? So this elementary matrix thing works, all right? Now, why would we want to do this? Well, it comes down to solving out these systems where we're describing them using a matrix. So we need to do things step by step. What are known as row operations. So let's follow the notes here quickly. So I'm going to write out this matrix A, and it's let's see, it's 1. Write this out element by element. 1, 1, 1, 12, 2, negative 3. And 3, 4, and 1. Okay. So we want to reduce this matrix down, right? Reduce this down to what's called row echelon form. And that's just, we want to write this out in a way where every row below the preceding one has at least as many zeros as the row above it that are leading. So a leading 0 is the first entry in the row is equal to 0. That would be called a leading 0. And so as we go down the rows, each subsequent row should have at least as many leading zeros as the one above it, if not more. That's called row echelon form. So how would we get this into row echelon form? So like we can do this step by step. So one way to do this, I'm going to take, if I take negative 12 times row 1 and add it to row 2, all right, so negative 12 times row 1 plus row 2. What does that give me? So I'm going to have the same row 1 because I haven't changed that, but row 2 is going to be a little different. It's going to be 12 minus 12, or 0, 2 minus 12, or negative 10, and then negative 3 minus 12, or negative 15. And then this row here doesn't change. All right, so now it's good. I've got a leading 0 here. All right, so far so good. But this isn't finished here. So we want to turn that into a 0 as well, so we can kind of start on this. So let's take negative 3 times row 1 plus row 3. And what does that give us? Well, we're going to have 1, 1, 1. We have 0, negative 10, negative 15. And then let's go back to this matrix here. Negative 3 plus 3 is 0. Negative 3 plus 4 is 1. And negative 3 plus 1 is negative 2. Okay? So we're getting closer. Now, how do I get a 0 here so I have more zeros that are leading in this row than above it? Well, we're going to have to take 1/10 of this second row and add it to the first row. So 1/10 of row 1 plus row 2. I'm sorry, plus row 3. And that's going to give us the following. Let's see, 1/10, that becomes negative 1. So if you multiply this all by 1/10, so negative 1 plus 1 is, let me fill this out, 1, 1, 1, 0, negative 10, negative 15, and then 0. Now, we're going to take negative 10, multiply it by 1/10, and add it to row 3. So negative 1 plus 1 gives us 0. What's 1/10 of negative 15? It's negative 1.5. Negative 1.5 minus 2 is going to be negative 3.5. And there we go. That counts as row echelon form. All right. Now, we can write out elementary matrices which do these operations for us. So for example here, if I want to write out this elementary matrix here, which takes negative 12 times row 1 and adds it to row 2, that elementary matrix is going to be E of 1, 2, negative 12. Okay? What about this elementary matrix here? It's going to be E. This should be 2 here, not 1. We took 1/10 of row 2, not 1. This is going to be E 2, 3 of 1/10. And then this one here is E of 1, 3, negative 3. All right. So what we can actually do, you know how we did this step by step, what we could actually do is we could put the elementary matrices in order, and what we would get then is if we had E 1, 2, negative 12 times E of 1, 3, negative 3 times E of 2, 3, 1/10, right? And then we multiply by this matrix here, A. Sorry, I was going to write out the whole matrix, but if we just multiply it by that matrix A, then the answer here is the following matrix: 1, 1, 1, 0, negative 10, negative 15, and then 0, 0, negative 3.5. All right? So we can actually line those matrices up. What do they look like if we actually write them out? If we actually write them out, you're going to get something that looks like this. It's going to be, you have to start with the elementary matrix, with the identity matrix, and work, we're going to work backwards, right? So it's going to be, so let me see, did I actually write that out correctly? Oh, I think I did that wrong. I'm sorry, guys. So we actually have to reverse the order here. My apologies. So it's supposed to be, let me write this out again correctly. So ignore this in your notes here, right? If you've been following along. So what we should have is e of 2, 3 of 1/10 times e of 1, 3, negative 3 times e of 1, 2 of negative 12 times matrix A, then that gives us our reduced matrix. Reduced echelon form. And if we write those out, what does this matrix look like? Again, it's the identity matrix, but we're adding 1/10 of row 2 to row 3. So it's going to be 1, 0, 0, 0, 1, 0, and then 0, and we're adding 1/10, right? What does this matrix here look like? It's negative 3 times row 1 added to row 3, so 1, 0, 0, 0, 1, 0, and then negative 3, 0, 1. And then we have negative 12 times row 1 added to row 2. All right, so 1, 0, 0, 0, negative 12, 0, it should be negative 12 because it's negative 12, 1, 0, 0, 0, 1. A lot of mistakes today. My apologies. And then times our matrix A, right, which was 1, 1, 1, 12, 2, negative 3, 3, 4, and 1. And if we were to actually go through those operations, it's simple, we can just go this one times that one, and take the result of that, multiply it by that one, take the result of that, multiply it by that one. I'll save you the details here because I don't know if I've got enough storage on my camera. What the result is that reduced echelon form matrix 1, 1, 1, 0, negative 10, negative 15, and then 0, 0, negative 3.5. All right, which is what we wanted. We wanted to have this into reduced echelon form. Right. Okay, another rule comes out of this, and that is that some matrix A, so keep a note here, that matrix A will be a square matrix. And if we have the system AX equals B, then this will have a unique solution for all B vectors if and only if when we get it into reduced echelon form, A has all non-zero rows. So reduced echelon A has all n rows as non-zero. Okay. So if we did this reduced echelon form operation on some matrix A, and let's say hypothetically we ended up with a 0 down here, then we don't have a solution for this system here for all B. Okay. And we want to have those types of solutions. All right, I'm going to end the video there so we don't get overwhelmed here. And the next video is going to start on matrix determinants, which is on page 11 of the notes. All right. Hope you all are following these video lectures, and we'll see. I'll update you on my health status, but as of now, things are a bit up in the air. All right. We won't be having class tomorrow, so I'll be sending an announcement out for that. All right. Take care, and we'll talk to you soon.